Okay, so for question 9, right, we are given this question where a boy, there's a there's a fruit that's going to drop on the boy, and somebody from far away is going to throw a projectile, right? The woman is going to throw a projectile to save the boy, and we're supposed to calculate what's the minimum speed that she has to throw the ball, right? So this is a very, very juicy question, and I'll tell you why later, because this with the right reference frame, right, it becomes very obvious. So anyway, this problem setup is as follows, right? We're given the boy over here, and above him there's a fruit. So the fruit is 10 meters above him. So I'll denote that by a letter B and I'll write 10. Okay? And there's a woman here, standing here, and she's holding a ball, and she's 10 meters away also. So I'll write that as A equals to 10. Right, the reason why I'm setting them to be A and B is because later on I'm going to generalize to scenarios where A and B are not 10. And you'll see specifically that A and B being 10 leads to a very nice answer, which is the goal of which is the which is and so the problem setter basically set these values so that the answer will be very nice. But in the general case, right, the answer is that there's some intuition to be made when we consider the general case, and I'll be analyzing the general case later. So anyway, the woman has a ball, so perhaps okay, this is a fruit over here, so I just add two leaves over here to mean a fruit and the ball that she's gonna throw, right? Um, so first, she's supposed to throw the ball such that it follows a parabolic trajectory and it hits the fruit as it's dropping down. So what does it mean for them to hit at this location X, right? This part where I hit, where I marked it out, what does it mean for them to hit? What it means for them to hit is that the ball's trajectory, right? The ball that the woman throws has a is described by a parametric curve x of t and y of t, right? And likewise, the fruit that's going to drop down is also labeled by x of t and y of t. Of course, x of t is constant, so we don't really care about that, but its y coordinate does change over time. So let's just denote this as um, x of b and y of b, right? And the other one would be y of f. Okay, so there exists a certain time, right? We want there exists a certain time t hit, right? I'll write t hit as a time. Let t hit be the time that the two items hit each other. So at this time, right? At this time, t hit must when they hit, they must satisfy two conditions. Right? One is that the x coordinate must match, and the other one is that the y coordinates must match. So xb of t hit must equals to xf of t hit, right? The fruit's x coordinate must equal to the ball's x coordinate, and the other condition would simply be would be y of b, right? The ball's y coordinate must equal to the fruit's y coordinate, right? Okay, so the first condition over here, let me just get a bit more space over here. The first condition is simply saying that let the initial velocity be u, right, and the angle be theta. Then the first condition is simply saying that u cosine theta times t hit equals to a, right? This means that after some time t hit, right, the initial horizontal velocity, the horizontal component of the velocity, right, is u cosine theta, and multiply that by time, then after t hit amount of seconds, the ball will have traveled horizontally a distance of a. Okay, so that's the first condition, and the second condition is that the y coordinates must match. So this one is a bit longer. It looks something like u sine theta t hit, right, minus half g t hit squared equals, so this is the ball's y coordinate as a function of time, right? After t hit seconds. Then for the fruit, it will be b minus half g t hit squared. All right. So you see something very nice over here, which is that if I take a look at these two equations, then one can realize that the half gt squared can be cancelled out, and what we're actually left with is an equation that can tell us the angle at which we need to project it by. So these two equations, right, u cosine theta t equals to a, u sine theta t equals to b. So if we divide it out, right, we see that the u and u's can be cancelled out. So what we actually get is tangent theta equals to b over a. And so if what we see is that the two conditions that must be satisfied if the ball were to hit the fruit is that the two conditions that must be satisfied can be translated into a condition on the angle at which the ball is projected. And there's something very nice geometrically about this angle. I'll show you. I'll draw it out now, right? So the conditions that they hit is actually a condition on the angle. And something remarkable is that we see that there's no mention in this condition. There's no mention of velocity. There's no mention of u, right? And there's no mention of t hit also, right? In other words, whether if you have the ball over here and it's thrown at an angle theta, right? Whether the ball hits the fruit, the fruit that's going to drop down, right? Whether the ball hits the fruit is only dependent on the angle at which the ball is thrown. So we have done the math, right? This is the math. But the geometric intuition is that tangent theta must be equals to height of the fruit divided by distance from the ball, between the ball and the ball's head, right? B over A. And if we draw it on the diagram, we see that is precisely, right, this angle of the triangle that is made by B and A, right? So in other words, if you are the woman trying to throw the ball to hit the fruit, right, the moment you let go of the ball, you should be aiming the ball at the fruit over here. And it doesn't matter how fast you throw it, right? You could throw it very fast, right, and let it hit over here. Or you could throw it very, very slowly and let it hit right before the fruit hits the boy's head, right? It doesn't matter. As long as you satisfy this tangent theta equals to b over a, as long as your angle is correct, right? Regardless of what velocity you throw it at, you will hit the fruit. And there's something, and this may seem like a purely mathematical fact, right? We seem like we just derived it analytically. But if the geometric reason, right, the physical reason, the physics behind this is that if we go into an accelerating reference frame, then this is very obvious, because if we go into what I'm going to call a rain frame, right, which is the frame that follows a raindrop as it falls. In other words, it's the frame accelerating downwards at an acceleration of g. In this frame, right, the fruit is stationary. And in this frame, right, the ball, right, remember the ball's trajectory is u sine theta t minus half gt squared, right? But if we are in an accelerating frame, then the half gt squared term is not there. So in this frame, the ball is traveling in a straight line. It's traveling in a straight line. And that totally makes sense, because we see that the condition that tangent of theta must be equal to b over a can be translated into a diagram right over here, where we draw the angle that the fruit makes with the ball at the initial time t equals to 0, and seeing that the angle that this fruit subtends, right, with the horizontal with respect to the ball must be this angle of the triangle, right? And that's what we derive mathematically. But this is obvious if this holds true. We get intuition for the math if we just go into the accelerating frame where we see that the ball here is stationary and this one is just moving in a straight line, right? In other words, constant velocity in the rain frame, in the frame that is accelerating downwards at g, right? If you're accelerating in the frame that you're accelerating downwards at g, you're kind of removing the effects of gravity, right? In fact, that kind of goes into the idea of general relativity and how acceleration is gravity, but that's a topic for another day. But in the rain frame, you're removing the effects of gravity, so your ball doesn't fall down, and your fruit doesn't fall down, and your ball just goes in a straight line because there's no gravity. And if the fruit hits the ball, if the ball hits the fruit in the rain frame, then because physics must be consistent throughout all reference frames, right? Whether the ball hits the fruit is independent of which reference frame you choose, right? Because of that, right? If the ball hits the fruit in the rain frame, the accelerating reference frame, then the ball must also hit the fruit in the lap frame, right? In the stationary frame where both things are accelerating at g downwards. So that's just some intuition for why the tangent of the angle must be equal to b over a, right? It totally makes sense in the rain frame. Okay, so anyway, now that we have explored the condition on the angle at which it must be projected at, right? Now we're free to answer the question. So the question once again asks if what was the minimum speed of the ball that she must throw. So once again, we draw the triangle. This is theta, this is b, this is a, over a is 10 and b is 10, right? But now I'm going to set a and b to equals to 10 because we're ready to answer the question and we're done with the geometric intuition. So tangent of theta. So in this question, since it's b over a, since 10 over 10 is just 1, and that implies that theta must be 45 degrees, right? Or pi over 4 radians. And so she's going to throw the ball at pi over 4 radians, right, at 45 degrees. And now all that's left to ask is, how fast must she throw the ball? If she throws the ball very fast, right, it's going to hit somewhere around here. If she throws the ball super slowly, right, it's gonna go something like that, and it's gonna actually it's gonna hit the fruit after the fruit goes past the boy's head, which still mathematically it holds true, right? Because they still meet at the same coordinates, but that's applied. If we take the math and apply it to this context, then we see that interpreting the math in this context means that if she throws it too slowly, the ball will have hit the ground, right? And the fruit will have hit the boy's head. So that's the minimum, since the angle is kept constant, right? The minimum velocity she must throw it at is the velocity such that it just nice, right, hits the boy. Just nice hits the fruit, right? Just nice hits the fruit right before the fruit hits the boy's head. So in other words, it must be a parabola that starts here and ends here. Okay. So yeah. So there's that. So we know that we know that equations will look something like that. So u sine theta, that's now we're considering the vertical component of velocity times t hit minus half g t hit squared equals to b, right, minus half g t hit squared. So this is when they hit, but we want the hitting to happen at height 0, right? At height 0. So if you substitute in this and the value of b into the following, you get t, a u over square root 2 t hit equals to okay, so equals to half g t hit squared, and yeah, so with this, right, we can see that and this must also be equals to 10. It must also be equals to b, right? So we have brought the half g t squared over to the right side. Yeah, so this is the case, and and so um and so we know the value of we can solve this equation. We want to find u, right? We want to find u, and we know values of g, we know values of b, we do not know values of t hit. So all that's left to do is to solve this equation, and we can do so by taking that u t hit. Okay, so let's solve for t hit first. So t hit equals to uh looking at this side of it, we have 2b over g square root. Okay, so 2 times b is 10, right? So that's 20. G approximately equals to 10 or so. So t hit is square root 2. And then after taking this, right, with b, we get u t hit, which is square root 2 now. Square root 2 over square root 2 cancels out, is equals to b. So u is equals to 10. And that's how we get A as the answer. Okay, but we see that most of the work was done when we derived that most of the interesting juicy parts of this question is this condition on the angle at which you must throw it by. We derived it from the math, but we can see that is the physical intuition comes from going into the accelerating reference frame. So we'll talk more about accelerating reference frame in the future. They can simplify calculations down greatly. And this is just a taste of the power that they hold. Okay, so that's question 9. Let's move on to the next question.